everybody, and welcome to our next video in Unit 8, which is all about weak acids and bases. So in this last part of the video, we started to calculate the pH of strong acids and strong bases. And that was relatively easy because the concentration of hydrogen ions or hydroxide ions, which of course is what determines the pH, is equal to the concentration of that acid or base, because strong acids and strong bases completely dissociate. So the reason why that occurs is because the value of K is very, very large. So remember, we are going to start tying equilibrium into this as well. So because K is large, therefore, if I was to determine the concentration of ions in this solution, so let's say I have a 0.1 molar barium hydroxide solution, we can use basic mole ratios and basic stoichiometry to determine what the concentration of hydroxide is. So in this case, it would be 0.2 molar. And the value for K is going to be very, very large. So because I'm producing a whole heck of a lot of ions, my concentration of products is much higher than my concentration of reactants. So K is very, very large. However, for weak acids and bases, we have to remember that these do not completely dissociate in water. So anything that's not one of those 6 strong acids or 6 strong bases, we can identify as weak. So for example, HC2H3O2, that's acetic acid. You don't have to memorize these, but you might start to because you're going to see them so often. But acetic acid is not one of those 6 acids, so we can infer that this is in fact a weak acid. As a result, when we think about that equilibrium value, that equilibrium constant is going to be relatively small. And that's because if I write this out right here, and we're going to call this our Ka actually, because this is the acid or the equilibrium constant for an acid, which you'll see down here, that's our acid ionization or dissociation constant. The Ka, because I'm dealing with an acid, is equal to my concentration of hydronium times my concentration of that acetate ion over my concentration of acetic acid. Because my concentration of hydronium and my concentration of the acetate ion is going to be very low relative to my concentration of acetic acid, my Ka value is also going to be very low. And the value of that K value, just like we did with equilibrium, will tell us how much something will dissociate. So the smaller the Ka means the less dissociation. Because as you remember, the higher the Ka, the more products you would have. So if the Ka is much smaller, you would have less dissociation. So as a result, because that value for K is so small, the concentration of ions in solution must be determined by the acid dissociation constant. Acid dissociation constant, which basically is just my equilibrium constant for that acid ionization. So we've talked about Kc, right? And that's what this was saying right here. So there's Kc. That's the equilibrium values when we consider concentration. Kp is for partial pressures. Keq is just a generic equilibrium. We talked about Kw, that's the equilibrium expression for water. Now we are introducing Ka, and Ka is the equilibrium constant if I have a weak acid, hence the letter A. So the Ka value, let's get this written down here, is, let's get rid of draw, go to the cursor, there we go. Acid ionization or dissociation, you could say either or of those phrases, is equal to, or this is defined as, equilibrium constant for the dissociation of a weak acid. So if I take a look at this is just a very generic example. So HA is just some weak acid, right? It doesn't matter what it is. This could be any sort of polyatomic ion. So a weak acid plus water gives us the hydronium ion, and it also gives us that conjugate base, whatever that is. If this is my acid, once it loses that proton, this must be its conjugate base. So my equilibrium expression would look like this, and it's just like we did with equilibrium. There's nothing new here. If you remember, right, water is not included in that equilibrium constant. So we don't include water because that is a liquid. So I'm not going to see water in any of these equilibrium expressions. This is our conjugate base that's over there. This is our conjugate. Not that you need to know that, but conjugate acid. However, I only use Ka when it's an acid, right? So let's say I have a weak base that is dissociating in water. So I have a weak base that's dissociating in water. This water is acting as an acid, which means it is donating a proton to the base. That base is accepting it. So this is our conjugate acid. And this is our conjugate base. Again, so my concentration of BH plus 1 times my concentration of that hydroxide ion over the concentration of the base is equal to the Kb. So this is important. Whenever I have an acid, we have to make sure that we use that equilibrium expression, and that's defined as the value of Ka. And if I'm using a base, that when I set up that expression, that is equal to the Kb. We have to make sure we keep that straight as we do these questions, because you're going to see that sometimes you do in fact need to switch from a Ka to a Kb. And it's actually quite simple to convert from Ka to Kb. This was one of your equations from before, but I kind of glanced over that. The Kw for water, so the acid ionization constant for water, that equilibrium constant, that's equal to the acid ionization constant times the base ionization constant. So that Kw, which remember is 1 times 10 to the negative 14th, that's equal to the Ka times the Kb. So just keep that in mind as we go through some of these problems. And because weak acids and weak bases do not dissociate much, remember their values for K will be very low, which we've already talked about already. Let's just go ahead and use this and consider, right, what would be the pH of these weak acids and weak bases. So it says calculate the pH and pOH of a 1 times 10 to the negative 3rd molar solution of acetic acid. And I'm given the Ka value there. I can't just take the negative log of that concentration. It's not the negative log of 1 times 10 to the negative 3rd. And that's because not all of this acetic acid is dissociating. So if I consider what is my reaction, that's dissociating into hydrogen ions and acetate ions. This concentration is 1 times 10 to the negative 3rd molar. Okay, that is not equal to the hydrogen ion because this is a weak acid. Not all of those are dissociating. So therefore, we have to figure out, well, what would that be? And I could determine that because I'm given the value of Ka, and that Ka is equal to 1.75 times 10 to the negative 5th. So let's write an expression out. Ka is equal to my concentration of the hydrogen ion times my concentration of the acetate ion, and that's over my concentration of acetic acid. Best way to solve this, use an ice chart, right? So ICE, never going to escape us. If I have a solution, my initial concentration is 0. Change, some amount of this is going to react, right? Or is going to dissociate. Some amount of that is dissociating, but that means that some amount of that is increasing and the same amount of my acetate is increasing. So my equilibrium amount is 1.0 times 10 to the negative 3rd minus x It's equal to x plus x. And since I'm given that value for Ka, right, I could set this whole thing equal to 1.75 times 10 to the negative fifth. Because this value for K is so low, just like last time when we took a look at equilibrium, I again can neglect that x. Makes the math quite a bit easier, right? So using that, let's just plug in all these numbers and find out what the pH is. Because if I know this value right here, let's get a different color. If I could determine what's that concentration, the negative log of that is going to give me the pH. So Ka is equal to, oops, let's get the actual value in there instead. So 1.75 times 10 to the negative fifth is equal to x times x over 1 times 10 to the negative third. And if I solve for x here, I'm just going to eliminate some steps. X is equal to 1.32 times 10 to the negative fourth. And remember, that's the molar concentration of the hydrogen ions and the acetate ions, but this is not going to give me the pH. Now that I know that this is my concentration of hydrogen ions, I'm running out of room over here, so I'm going to continue up top. I'm going to take the negative log of that value because that should give me the pH. And pH is equal to 3.88. I'm missing a sig fig there, and I don't feel like taking out my calculator, so 3.88 is fine. pOH would be 14 minus that. So 14 minus 3.88 is going to give me 10.12. So notice how if I were to take the negative log of 1 times 10 to the negative third, I believe I would get 3. This is not that acidic. It's not going to have that low of a pH because not all of those acetic acid molecules are dissociating. You're going to have less that's dissociating, which raises the pH a little bit. And that's the whole idea behind everything that we're going to do here. So, yeah, let's continue with the next one. So the basicity constant, Kb, for ammonia is 1.75 times 10 to the negative fifth. And notice it does say it's only coincidental that it's equal to the Ka for acetic acid. That was not done on purpose. So it says calculate the pH and pOH for a 1 times 10 to the negative third molar solution of ammonia. So ammonia is NH3. It doesn't really matter how we write this out. We'll add a water there. Since technically, remember, everything is in water. If ammonia is acting as a base, right, that means it is accepting a proton. So my products would be ammonium and hydroxide. Now you could technically also do this up here. So if you add water to this side, this would technically be your hydronium ion, but the work ends up being the same exact thing. So I normally like to do it for bases here because I like to see the production of that OH group. If I don't have that, if I don't have water here, I don't have a balanced equation. So again, you'll start to see some of my tips and tricks as I go through this. I have an initial concentration of ammonia, and this is a weak base. And I know it's a base because it's giving me the value for Kb. So if it gives you the Ka, you know that's an acid. If it gives you the Kb, you know it's a base. So let's see. 1 times 10 to the negative third. This is water, so we don't have to worry about that. 0, 0, minus x, plus x, 1.0, 0 times 10 to the negative third. I can, again, neglect that x, and I could do that for all of these because that value for K is so small. So let's go ahead and we'll actually get the same exact work, but I want to show you how this one is just a little bit different from this one up here. So my Kb is equal to 1.75 times 10 to the negative fifth. And that's equal to x squared over 1 times 10 to the negative third. And just like before, I'm getting the same exact thing. I get 1.32 times 10 to the negative fourth. Now, this is my concentration of hydroxide ions. So here's where you have to be careful, and it starts to get very important to write out your formulas for everything. Because if you stop writing out formulas, I think it's easy to start getting confused. So make sure you carry those formulas throughout. Because if I take the negative log of this number, right, I'm going to get a value of 3.88. But that's not the pH in this case, because I took the negative log of the hydroxide ion concentration. So 3.88 is my pOH in this case. My pH, which is 14 minus 3.88, gives me 10.2. So you have to be careful as you do these problems. It's very easy to kind of get lost in the work because you have pOH and pH and negative log of this versus negative log of that and Ka and Kb and oh my gosh, right? Try to be as organized as you can. It is very important, especially in this unit, I think, to be as concise as possible when we are writing these out. C, nicotinic acid or niacin. I use it a lot in vitamins. Is a monoprotic acid. Monoprotic, so that's one. Mono means one. Protic, of course, is a proton. With a formula of HC6H4NO2, a solution that is 0.012 molar in nicotinic acid has a pH of 3.39. What is the Ka for this acid? Let's write an equation out. So let's see, HC6H4NO2, and that's dissociating into hydrogen ions. And I know because it's an acid because it's giving me the Ka, right? Or it does say acid as well. So I know that that proton in the front's coming off. C6H4NO2 minus 1. So I have 0.012 molar, this, and I have 0, 0. Now you don't have to technically write all of this out. You'd have minus x, plus x, plus x, 0.012, right? And that's minus x, you can neglect that. And you have x and x. However, you are given the pH of this system. So remember, the negative log of the concentration of hydrogen ions is going to give me the pH. So since I'm given the pH, I could determine what is x equal to. And my last video, I'm so mad. I realized this today that I did the wrong operation, right? But you would do 10, the anti-log, right? You do 10 raised to the negative 3.39. I'm so mad at myself that I did that. But it happened. So answer is 4.07 times 10 to the negative fourth molar concentration of hydrogen. So that is equal to this, which is also equal to this. And now that I have all of those equilibrium concentrations, I can plug those into my equilibrium expression and get the value for Ka. So let's go ahead and do that. Ka is equal to 4.07 times 10 to the negative fourth times 4.07 times 10 to the negative fourth over 0.012. And I get a Ka equal to 1.38 times 10 to the negative fifth. So if I just compare, right, let's just take this and compare this to acetic acid. Who dissociates more, right? Does niacin dissociate more, or does acetic acid dissociate more in solution? if you compare those Ka values, the Ka for acetic acid, granted not by much, it's not that much higher, but it is a little bit higher. As a result, your concentration of products would be a little bit higher for acetic acid. Therefore, acetic acid does dissociate a little bit more. Let's take a look at D. So what are the concentrations of nicotinic acid, hydrogen ion, and nicotinate ion in a solution of 0.1 molar nicotinic acid? And what's the pH? And we determined the Ka in this problem. So we're just going to use that value here. I have HC6H4NO2 in equilibrium with hydrogen ions. And whenever you have your conjugate base, a lot of times the name of this is going to end in ATE. So if I have acetic acid, what's left is my acetate ion. If I have a citric acid, that ion that dissociates from that is called citrate. So in this case, because I have nicotinic acid, what dissociates from that is the nicotinate ion. So whenever you see ATE, a lot of times that's going to indicate that that's its conjugate base. And that's just that ion, whatever's left over after that proton has dissociated. So I have 0.1 molar of that. And I'm not going to write the workout because this would be just X and X. You don't have to set up an ice chart every time because you're going to start to see kind of how this works. And I want to know what's the pH of the solution. And in order to determine the pH, I have to know what's the concentration of this guy here. So I have my Ka, 1.38 times 10 to the negative fifth. It's equal to X squared, essentially, over 0.01. X is equal to 0.0011 molar. That is my concentration of that hydrogen ion. So if I want to know what's the pH, all I have to do, take the negative log of this number. And when I do that, I get a pH of 2.96. Not bad, right? We're bringing back that equilibrium. And I think this is the easy part of equilibrium, really. The only thing that we have to do after that is just take that negative log to determine the pH. Or if we're given the pH and I want to know Ka, you have to take the anti-log of that. So let's try E. So morphine is administered medically to relieve pain. It's a naturally occurring base, or it's an alkaloid. What is the pH of a 0.0075 molar solution of morphine at 25 degrees? And we're given the value for Kb. So this is a base. So let's write an equation out first. C17H19NO3. I'm going to react it with water. Like I said, only because if this is the base, this is the acid, this must be donating a proton to morphine. And it doesn't matter how you tack that extra hydrogen on. I'm just going to throw it in the front just because it's easier that way. You should, however, always do a +1. And then I have my hydroxide ion that's left. So let's see. All right, so I have a 0.0075 molar solution. Some amount. And let's use that Kb and calculate what my hydroxide ion concentration is. So I don't have to convert this to Ka because since this is a base, I have to have hydroxide in there somewhere. So that's why you can use Ka or you can use Kb, depending on if it's an acid or a base. But you just have to be careful because if I take the negative log of this when I'm finished, that's going to give me the POH. Anyway, so we're given the Kb, 1.6 times 10 to the negative 6 is equal to X times X over 0.0075. And my value for X in this case is equal to 1.1 times 10 to the negative 4th. And that's equal to my hydroxide ion concentration. So if I take the negative log of this number, that's going to give me the POH, which in this case is equal to 3.96. However, the question was asking for what is the pH. Again, I don't know why we use POH, it's so silly, but it's whatever. But to find the pH, it's equal to 14 minus 3.96. Gives me a pH value of 10.04. Again, it's all equilibrium, right? We're just taking it that extra step with calculating the pH. Let's talk about the strength of acids and bases. We're almost done. We're going to finish this page and we'll go from there. So what we can do to kind of compare the relative strength of acids and bases is by looking at what's known as their pKa. So like we said before, we compared the Ka of acetic acid versus we compared the Ka of that nicotinic acid. So I think we could compare A to C. So in this case, because acetic acid has a slightly higher Ka, that means that acetic acid is a slightly stronger acid because it dissociates into more hydrogen ions. And we can see that by looking at our values for Ka. So the higher the Ka means the more dissociation that occurs. But the lower the Ka means that dissociates less, right? And what we can do, now I don't know why chemists do this. They have like 800 ways to measure the same thing. And it drives me nuts sometimes. And this is one of those things that I just never really got in my brain as to why we measure it this way, but we do. So it is what it is. This would be something, personally, if I had the AP exam in front of me, I would have to remember that the higher the Ka means the lower the pKa, which means the stronger the acid. So actually down here, we can write stronger down here. So the pKa value is one method that's used to indicate the strength of an acid. So we could see here, the higher or the lower the lower Ka means the higher the pKa. And the higher the pKa means the weaker the acid, right? So if I compare that to here, the higher value for Ka means the lower pKa, which means the stronger acid. Now, if it were me, I would just say, okay, the higher Ka means the stronger acid because that means more is dissociating. Why chemists had to take it a step further, I'm not quite sure, but they tend to like to use the pKa. And the way you can calculate the pKa is by taking the negative log of the Ka. So notice both sides of this equation have Ka. The negative log of some value is equal to the pKa, or is equal to the P of whatever that is. So let's say I have the negative log of the Kb value that equals the pKb. Okay, the negative log of the hydrogen ion concentration is equal to the pH, right? So the negative log of whatever is equal to the P of whatever I'm measuring on the other side. Lower pKa means the stronger the acid. Again, this is something that you'll have to compare on your exam, and you have to know that. So I would highlight this, get it ingrained in your brain. The day of the test, I would write this down somewhere. I don't know why. It's just something that never stuck with me, but you have to know it. Anyway, let's go ahead and talk about percent ionization or dissociation. So calculate the following percent ionization or percent dissociation of acetic acid in each of the following solutions. So what we can do is compare, if I have some initial concentration of acid, what percentage of that concentration is dissociating? And we can compare what's known as a percent ionization. So if you think back to, percent composition and the percentage of something in a mixture, you take the percentage of whatever you're looking for and divide it by the total. And that's what we're doing here. So if I want to know what percent of that initial amount ionized, I would take the amount that dissociated and divide that by the initial concentration. and times that by 100. So what we're going to do is I have two solutions of different concentrations, but of the same material. It's both acetic acid. And let's compare what happens to the percent ionization with varying concentrations of this acid. So almost done. I have HC2H3O2, and that's in equilibrium with the hydrogen ion. And I have the acetate. So again, because this is the conjugate base, it's acetate ion. And I have 1 molar of this, and I have some amount of hydrogen and some amount of acetate. And I'm given the Ka. So let's determine how much of my protons is dissociating, right? What concentration of this is dissociating? So we can use my value for Ka and figure that out. So 1.8 times 10 to the negative fifth is equal to x times x over 1. And you solve for that, and you find x is equal to 4.2 times 10 to the negative third molar. So that's my concentration of hydrogen ions. So that must mean that that concentration is how much had dissociated. So to find my percentage of ionization or my percent dissociation, they mean the same exact thing in this case, I'm going to take my concentration of whatever dissociated, and I'm going to divide that by the initial concentration, because this percentage of the whole is giving me what percentage of the ions broke apart. Times that by 100, and I would find that 0.42% of those one mole of acetic acid molecules have dissociated. So that's essentially like 1 per every 200 have dissociated. Let's go ahead and do the same exact method, but in a lesser concentrated solution. So I'm going to rewrite my equation. HC2H3O2, H plus 1 and C2H3O2. But here I have a slightly less concentrated solution. I'm going to solve this the exact same way because it's the same exact material, so the Ka is the same. 1.8 times 10 to the negative fifth equal to x squared over, but in this case, my initial is 0.1 molar. Value for x is equal to 1.3 times 10 to the negative third. So now if I want to know my percent dissociation here, I'm going to take my 1.3 times 10 to the negative third molar. That's the concentration that has dissociated. And I'm going to divide that by my initial concentration. And I find that 1.3% of the acetic acid in this example dissociated, 1.3% dissociated, and in this example with the higher concentration solution, only 0.42% dissociated. So in this case, you could see that the solution that is lower in concentration actually dissociated more. And that's because no matter what, you're going to have the same number that's dissociated because your Ka value is the same for both of them. So the lower the concentration of the solution, the higher the percentage of those ions are dissociating. So the lower the concentration, this is important to know, the lower the concentration of solution means the higher the ionization or dissociation. I feel like a lot of times with this, you would see like a free response question like this. It would give you 2 examples of solutions, and it would say which one would have the higher percent ionization, justify your answer, right? So the lower the concentration typically has a higher ionization, and that's because a higher percentage of those is dissociating in the solution. Sorry, I know it was another relatively long video. Hopefully when I edit this, it goes down a little bit. But otherwise, I will see you in the next video, which we're going to start to talk about buffers, and those are a lot of fun. So I will see you then. Bye.